Yayın başlıyor diyor.
22 saniye
Canlı
geç geliyor.
yayındasın. Sayfayı yenileyim bakayım. Neymiş? Bu görüntüde bir şeyler oynadım da görüntünün nasıl görünüyor bir emin olduktan sonra bırakacağım. Evet. Görüntüde bir patates var, onu düzeltelim. Çünkü full ekran, yani biraz büyüttüm ekranı, şey olmuş.
Bakayım ben de açayım. Ses yankılanabilir. Hello. Yok.
Şu an YouTube'da
Görünüyor.
görünüyor
Hello.
ya.
Görünüyor
Ama
ama Discord ekranı.
Yok o biraz gecikmeli geliyor sana sanırım. Sadece boyutlarda bir sıkıntı vardı, onu düzelttim de geriden geliyor herhalde o da. Şu an YouTube'da
Görünüyor.
görünüyor ya.
Görünüyor ama Discord ekranı.
Yok o biraz gecikmeli geliyor sana sanırım. Sadece boyutlarda bir sıkıntı vardı, onu düzelttim de başlayabilirsin istiyorsan sen.
Okay. Hello everyone. My name is Berk Agin. So I am Master of Student at 9 Eylül University and Reinforcement Learning Researcher. So we will talk today Trust Region Optimization and Proximal Policy Optimization. And we get started with introduction and we will talk about surrogate function of these algorithms and continue with TRPO and Proximal Policy Optimization. And we will see some example codes and pseudo codes of these algorithms. And we will finish today. Student at the purpose of these algorithms to solve. So we will talk some example codes to making it very challenging. And policy gradient also, as I said, this here. And what are we optimizing? We are optimizing that the expected probability of policy in here. So a hat is here advantage function, and advantage function says as to how choice of the action is good or bad. And we can define loss of policy gradient by differentiating the objective in the following mathematical expression. And this is obtained by differentiating the above mathematical expression. And so what does policy gradients do? It is an optimization problem that allows you to do a small update to policy based on data sampled from policy on policy data. So we will see today TRPO and Proximal Policy Optimization, and these algorithms are on policy optimizations algorithms. And after that, we try to optimize policy in order to obtain maximum reward. So in reinforcement implementations, the cumulative reward is the essential. So we try to obtain the maximum reward, and expected reward is here discount in here. So discounted reward, because of that, the future states will affect less than the current state. The discounting factor, the purpose of the usage discounting factor. And where RT is the ratio between new and old policy. So after we obtain the current policy, then we have to ratio to old policy, because we take an advantage and correspond the between these old policy and new policies. And after that, what is the surrogate function? Actually, surrogate function is similar to objective function, but we have to consider that the main purpose of optimization problem. Then the challenges of policy gradient methods. In reinforcement learning, we optimize a policy for the maximum expected discounted rewards, as we see previous slide. And nevertheless, there are few challenges that hurt policy gradient performance. And first, policy gradient computes the steepest ascent direction for the rewards and update the policy towards that direction. And however, this method uses the first order derivative and approximates these algorithms in here. And one policy, we have to collect the trajectory before optimizing, and step leads to a. But if we step is too small, the model learns too slow. And as you can see in here, if you step too large, and you will go to the in air, then you have to be careful. But if you choose the step size is very small, and it will be process will be very slow, and this is not optimal solution for these algorithms. You have to choose very wisely in here some hyperparameters. Then if the policy goes too far, it takes actions that too far and pull off from the cliff. As we resume the exploration, we start from a poorly performing state with a locally and bad policy. The performance collapses and will take a long time, if ever, to recover. Then after this slide, so we can see that minorize and maximization algorithm. So M is a lower bound for policy in here. So this is an Kyle divergence parameter, and we will see after some slides. And loss functions in here, and it's equal to M parameter. So we are trying to reach optimal policy for every step. This is the current policy, and the eta theta for the policy, current policy, the red line in here. So the theta star is an optimal policy for reinforcement learning in reinforcement learning algorithms. So after each step, so we try to optimize, we try to update this M function to optimal policy, and we are trying to approach this point. Then after that, so MM is an iterative method. So for each iteration, we find a surrogate function. So surrogate function, as we said before in here, M, and that is a lower bound function for current policy, and actually easy to optimize. So we will approximate the surrogate function as a quadratic equation. So in each iteration, we find the optimal point for M and use that as the current policy. Then we re-evaluate a lower bound at the new policy and repeat the iteration. As we continue the process, the policy keeps improving. Since there is only finite, our current policy will eventually converge to the local or the global optimal point. And this is the previous slide in here. So this is the final demonstration in here. with safe iteration, it keeps moving and finally converge optimal policy. Then let's pass to trust region optimization. Trust region optimization it uses an objective function in here. So we train to maximize policy with these parameters. So advantage function is also used in here, and this is ratio between current policy and old policy, subject to Kyle divergence between old and current policy. But this is the very important point. In the delta parameter constraint that the step size for trust region optimization. So delta is hard constraint parameter. After updating our objective function, we control that the step size in here. So it provides us to safely update. So Kullback-Leibler divergence consists that probability distributions as following mathematical expressions. This is a quadratic function and second order function, and we can say that this is a good solution, but it's not easy to understand totally. So as we say it in here, objective function, the natural policy gradient in natural policy gradient and TRPO and proximal policy optimization starts with these mathematical expressions. In short, we want to maximize the advantage function. So the expected rewards minus a baseline to reduce variance, but we apply a constraint that the new policy cannot be too different from the old policy. The remaining of here, and it will the remaining of mathematical expressions will explained in John Schulman articles. So after Kyle Kullback-Leibler divergence, so possible to use penalized instead of hard constraint. So this provides us more smoothly updating, but it's in proximal policy optimization. It is not chosen frequently because that some parameters are simpler in proximal policy optimization. So in practice, in here delta is easier to tune, and fix delta is better than fix beta.
Can you hear me?
Yes, I can.
Somebody had one question about this slide, so I'm just reading it.
Okay.
Is the delta is like the threshold for the convergence? He asked about the delta parameter on the last slide, I think.
Yes, we can back turn, and yes, it's true. It's threshold for in trust region optimization, but we will prefer other parameters instead of these parameters, because in some practical algorithms or in some applications, the other ones are simpler and more efficiency from this one.
Okay.
Then yes, this is a demonstration to understand easily trust region optimization. So this is the first point of the policy, and after updating the policy, we will continue to the peak of the cliff, and in order to control learning speed, the delta parameter is essential. But we will firstly see the trust region optimization, and as you can see, the trust region optimization and proximal policy optimization are 3 years old algorithms. Some new algorithms, more efficiency in here, but it's very essential also reinforcement learning algorithms. Then after this one, so let's talk about the limitations of trust region policy optimization. And hard to use with multiple outputs such as policy and value function. So we have to design that with some parameters, same parameters actually in same state. So need to weight some different parameters. So policy uses state action pair, and value function also uses state. So empirically performs poorly on tasks requiring deep CNNs and RNNs. So I took that this sentence from John Schulman RL Bootcamp slide. John Schulman is a person who study on reinforcement learning, and he is very clever and experienced person. So after some results, he took in sentencing here. So we can say that some deep reinforcement learning algorithms must be faster to compatible pixels for these frames, and we have to obtain more speed, computational speed. Then let's pass the proximal policy optimization. Proximal policy optimization is simple than trust region optimization, and good idea also. Then we can see that in here, and so you can see that the form of lower bound with clicked importance ratio. So this is the you can use the variance parameter, but also you can use the penalized variant in here, but it is used in the trust region optimization more frequently. Then in proximal policy optimization with clipped objective, we want to use a first order optimizer like the gradient descent to optimize our problem with a soft constraint to penalize the objective if we change the policy too large. In implementation, we maintain two policy networks. So the first one is the current policy that we want to verify. Then the second one is the policy that we last use to collect samples. As you can see here, so this is also essential for these algorithms. And with the idea of importance sampling, we can evaluate the new policy with samples collected from an older policy. This improves sample efficiency. Then we construct a new objective function to clip the estimated advantage function if the new policy is far away from the old policy. The new objective function is in here. So where hyperparameter is epsilon. So this is new parameter, what we use instead of the delta, as you can see the previous slides. So it guaranteed that step size for safe update, like other constraint, but this is more simpler to other one. And advantage function, if advantage function gives us the positive value, and our update goes to the positive direction, and this is our parameter ratio. Then we constrain with this plus and epsilon 1 plus epsilon line. And epsilon is a very small parameter, but this is a very cleverly in here. Then the best option for epsilon 0.02, I think, yeah, 0.02, according to the John Shillman's results. Then, as you can see, advantage function. If advantage function gives us the negative value, then it goes to the 1 minus epsilon, but it comes from in here. It comes from in here and limited with 1 minus epsilon. Then we can say that effectively this discourages large policy change, and we can control that in here. So what about in pessimistic scenario? So I mean that the pessimistic scenario, what is the largest step size? So as you can see here, there's some different functions. So and its results. So linear interpolation factor is the ratio, and it clipped expected advantage function and clipped with epsilon, and it's limited in here. So we can say that the best option of these algorithms. So as you can see, without any constraint, it goes to the infinitive, and it's not possible to converge in here. So performance of one updated iteration is under safe via clipping for current policy and Kate policy. Then, according to the result of Proximal Policy Optimization by John Shillman and et al., these are some different environments from OpenAI and Jim. So as you can see, the Proximal Policy Optimization with clipped parameter gives us good results in here. So as we compared with trust region policy optimization, and you can see swimmer environment, trust region policy optimization gives better result. Then let's pass some codes implementation in here. So these are steps for trust region policy optimization. So there are some hyperparameters for child divergence, such as delta, and some trajectory parameters, learning rate or step size, as we can use the policy gradient, and some also affects that the results directly. So we will see that some effects after this slide. Then wrapping up. So TRPO is on policy algorithms, as we said before. So to constrain step size, it uses child divergence as hard constraint or penalized. So we have two choices. We can use hard constraint or penalize. Then TRPO is equal to natural policy gradient plus line search plus monotonic improvement theorem. So this is the summary of the TRPO. After that, we will see that the proximal policy optimization clip. So input initial policy parameters, initial value parameters, we initialize these parameters. After then, we can start the collect of trajectories by running policy from the environment and compute rewards and compute advantage estimates. Then we can optimize the policy according to the advantage function and these rewards values. So update the policy, maximizing proximal policy clip objective. This is mathematical expression that we see. Then after that, the fit value function by regression on mean squared error. It also use this regression function by then the other optimizer can be used in here. So to wrapping up, proximal policy is also an on policy algorithm and easy to implement and good idea, and can be used with two different variants as penalty and clipped version, such as TRPO. So let's see that some implementation in here. So we can pass OpenAI GitHub repository. So this is the proximal policy, the stochastic gradient descent simplify. And after some collection, so we can pass the optimizing part. Then this is the optimizing part. As I see, the OpenAI uses in Adam optimizer in here. So it calculates according to the advantage function, target function, and observations. So Adam optimizer in here. So I can show that some mathematical expressions in here. So ratio defined as is defined as using TensorFlow mathematical libraries, and surrogate function one using in here ratio multiplying with advantage target function, and this is the clipped parameter for this one. But this is proximal for proximal policy one. The TRPO is different. It's not used for transition policy optimization. And as we can say before, it's easy to implement proximal policy optimization in here. Then also it uses the first order expression, and we can go to the happiness for optimization. Then let's back TRPO. So yes, as we said before, there are some parameters for trust region optimization, and KL divergence parameter and surrogate functions calculated in here, and so improvement is more important for controlling the step size, and surrogate minus surrogate before in here it must be controlled. Also, we can say that the delta, so delta, yeah, delta in here. So this is web prediction, non-terminal, and web prediction. But this delta actually, this delta used for calculating advantage target, and in here. So this is also OpenAI code, and you can reach that baseline and TRPO MPI with visiting GitHub. So let's back to the slides, and yeah, it's finished. So do you have any questions?
I have one, I think.
Yes.
When you like approach a problem, how do you like go choose your algorithm? Do you go like PPO directly at the first try, or you look some other projects? How do you approach PPO, or use PPO or not?
Yeah, actually, I used Proximal Policy Optimization is the first algorithm I implement in my project, but there are very different results also. So you can use very different algorithms to reach the most the optimal policy and change some parameters. So I can say that some parameters are effectively very important, because exploration and exploitation is the dilemma for reinforcement learning, and epsilon parameter also epsilon parameter is most important to reach the this exploration area. Then I use this one with changing some parameters and trying to solve some problems, I can say.
Thank you. And
You're
you
welcome.
also mentioned other algorithms surpassed the performance of these papers, because
Yeah,
they
in
are
here.
like 3-4 year old now, and but they still kind of proves successful results. So what do you think about that, like personally?
Yes. So these algorithms developed very cleverly, and some changes also it can they can give some better results. So the alternatively to trust region optimization, I read the article before. I read the article before implement. So what is the name? Then separated trust region optimization also. It published after 2 years from trust region optimization, and it also gives better results in some environments. It depends on some environments. Results can be changed. Then we will continue try, develop, and observe the results.
Thank you. And
Okay.
I don't think we have any more questions. Thank
Yes.
you for your presentation today.
Thank you.
And hope you people enjoyed it. We will also record this so you can watch it later on and rewind, rewatch, etc. And if you have questions, you can reach us relating this. And thank you.
Have a nice day.
Yayını sonlandırdık.